Hello, this presentation is part of my study on antenna, and today's topic will cover key concepts in antenna theory, specifically radiation intensity, power density, and directivity. And these are fundamental to understanding how antennas radiate energy and how efficiently they do so. So let's talk about the electromagnetic field in the far field zone. First, the equation shown here represents the far field approximation of the electric field. And this simplifies the field representation at large distances from the antenna. In this region, the R dependence separates out, leaving a simple expression like e to the power minus jkr by r. And this indicates that the amplitude decays as 1 by r and the phase term is e to the power minus jkr. Only the angular components theta and phi remain significant in the field expressions, meaning that e theta not and if I not describe the directional characteristics of the radiated field. So on the right here, we can see a coordinate system diagram illustrating r, theta, and phi, showing how the antenna radiates energy outward. Understanding this concept is crucial because it allows us to analyze and model antennas efficiently by focusing on these angular components in the far field. Now let's look at the magnitude of the electric field. Here the equation here shows the squared magnitude of the electric field, and this tells us how strong the electric field is at a given point. Essentially, this is the power carried by the electromagnetic wave at a given distance. And the term 1 by r square is crucial. It shows how the field strength decreases with distance from the antenna. As we move into the far field zone, the field strength falls off proportionally to 1 by r square. And the diagram on the right illustrates this concept, showing how the field expands outward and weakens as it moves into the far field zone. Here the Poynting vector, which represents the power density of an electromagnetic wave. Here the first equation here, and this equation shows that power density is determined by the cross product of the electric and magnetic fields. The Poynting vector gives us the power flow in units of watt per square meter, and in the far field, this vector points radially outward from the antenna indicated by R. Also, in the far field region, the electric field and magnetic field are perpendicular to each other and to the direction of propagation. So here we can see a simple 3D diagram illustrating E and H perpendicular to each other and pointing in the direction of power flow. Now, finally, let's discuss the power density in the far field. The key equation here is the first equation. Here, eta naught is the intrinsic impedance of free space, which is approximately 120 pi ohms. This equation represents the power density, the rate of energy flow per unit area in the far field region, and it's given in watt per square meter. Notice that in this region, the power density points radially outward from the antenna, forming spherical wavefronts. And the diagram illustrates this concept. Each arrow represents the Poynting vector, indicating how power spreads uniformly in all directions. Understanding this helps us quantify how an antenna radiates energy into space. Now let's explore radiation intensity, which is a measure of how power is distributed in different directions. Here the key equations is the first one, where W is the power density, and alternately using electric field components the second equation, and this relates the radiation intensity to the squared magnitude of the electric field. Radiation intensity gives us the angular distribution of power. So how power varies with angles theta and phi. The units are watts per steradian, representing the power radiated per unit solid angle. So here the diagram shows a cone-shaped section of space, illustrating the concept of differential solid angle D, the angle, mm, and how power radiates in different directions from the antenna. Now let's look at the solid angle. Here the equations, the first equations, this represents a small portion of a sphere in terms of the angular coordinates. It helps us understand how power flows through a specific cone of angle theta and phi. Think of it as a slice of a sphere, helping us analyze how much energy is radiated in different directions. So the diagram shows this concept visually. The yellow segment is a small patch on the sphere's surface defined by theta and phi and represents the solid angle element d ohm. This understanding is essential for analyzing antenna radiation patterns and calculating total radiated power. Now, the total radiated power, which is the total power radiated by an antenna, and this the equation integrates the radiation intensity over the entire spherical surface. It tells us the total power radiated by the antenna in all directions. The units of P radiation are watts, representing the cumulative effect of all directions. So that so here the diagram shows this concept with the sphere. The shaded portion represents a small solid angle, but the integral is performed over the entire sphere to get the total power output. Now the directivity, which measures how focused an antenna's beam is. Here the first this formula compares the directional radiation intensity E of theta phi to the total power radiated by the antenna. Essentially, directivity tells us how much more power is radiated in a particular direction compared to an isotropic antenna which radiates uniformly in all directions. A higher directivity means a narrower and more focused beam, which is important for applications like radar and point-to-point communications. Here the diagram illustrates this concept. The isotropic radiation is shown as a circle, while the directional radiation is shaped like a lobe, indicating more energy radiated in certain directions. Now let's talk about directivity in decibel, which is a commonly used scale in antenna analysis. Here the equation is the first equation. This converts the directivity value into decibels. The decibel scale is useful because it allows us to easily compare antenna performance, especially when dealing with large differences in directivity. For example, a 3 decibel increase means the antenna radiates twice as much power in a given direction compared to an isotropic source. On the right, the table shows that the 3 decibel equals a factor of 2 and 10 decibel equals a factor of 10. Understanding directivity decibel helps us evaluate and compare antenna designs more effectively. Let's wrap up with a summary of today's presentation. Like first, in the far field zone, the E field and H field decouple, making the analysis simpler. Here we learned that power density is given the equation representing the power flow per unit area. Radiation intensity helps us understand how power is distributed in different directions. The total power is calculated by integrating the power density over a solid angle. Finally, directivity allows us to compare the antenna's performance to that of an isotropic radiator with higher directivity, meaning a more focused beam. These concepts form the backbone of antenna theory and analysis, helping us design and evaluate antenna systems effectively. That's it for all today, and thank you.